Alright, wonderful. Hello. This will be the first lesson in a number of lessons in which we will cover electric circuits, the fundamental concepts, and a lot of the basics, going through numerous examples as we explain different concepts. This lesson will be going through the concept of voltage, current, and resistance, as well as power and the passive sign convention. The textbook that I'm utilizing to find these fundamental descriptions is the 10th edition of Nilsson and Riedel. I found this book to be rather helpful and descriptive, and there's numerous examples from which you can work from. Normally, you'll find that the literature describes current, voltage, and resistance using the analogy of water. So see that we have this pipe, and we define the current as the water or the charges flowing through this pipe, or we would call it a conductor. So that is the current, the charges flowing through the conductor. Then we have resistance, which is denoted as R, which hinders or impedes the flow of this current. And finally, we define voltage as the force, so the pressure that this water or the charges are experiencing that forces the flow of current through the conductor. There are certain fundamental concepts within electric circuitry. We define charge as being bipolar. That means that every charge has a positive and a negative side. As we can see here, voltage, positive, negative. And that all charge is discrete multiples of the electronic charge. So the electronic charge is 1.6022 times 10 to the minus 19 coulombs. And we can describe all electrical effects as the separation of charge and the flow of charge. Today we'll be mainly dealing with the flow of charge. Okay, let's now describe what voltage is. We define voltage in its differential form as the variable V dW over dQ. So this is the energy per unit charge. And the units for this will be joules per coulomb. So it's the amount of the energy or the potential difference over a certain area of a conductor or over a certain element within an electric circuit. And this will become clear once we define certain elements within electric circuits. So this voltage is the unit volts or joules per coulomb. Usually we use volt. Let's define current in its differential form as I dq dt. So current is the rate of charge flow. Obviously we can see charge per unit time. So it's the amount of charge or the current flowing through a certain position within our electric circuit or area within the electric circuit. The units is coulombs per unit time, and we denote it with the symbol A for ampere. Alright, let's move on to resistance. So resistance we define as the impedance to flow of current. A resistor in our circuit is usually denoted as one of these two symbols. Within our work, I will be using this top symbol. We define R over it. So each one of these resistors will have a certain value in ohms. Now, since we've said that this resistance is the impedance to flow of current, we can denote this relationship, that R is inversely proportional to I. And what comes out of this is Ohm's law, where our resistance value is equal to the voltage over a certain element divided by the current going through that certain element. So we can see that this relationship still holds, that the resistance is inversely proportional to the current. So the higher the resistance, the less current will flow through a certain element. And these three essentially fight one another to balance the circuit. So we can note that we can write Ohm's law in three different forms: V equals Ri, as well as I is equal to V over R. Wonderful. A typical way that we would write this equation is within this triangle. It's just simpler to remember, and this describes the relationship between the three fundamental variables. Now, let's describe the passive sign convention. This is really fundamental to circuit theory, and initially it may seem confusing, but it's just a convention to standardize whether or not a circuit element is absorbing power or delivering power. And it's something that you learn, and eventually it really, with enough practice, it makes a lot of sense. So let's define this resistor R1 and another resistor R2. If we define a current I1 flowing into the positive terminal of V1, then we can use Ohm's law to calculate any one of these variables, given that we have the other two, simply like that. However, if we define I2 flowing in the opposite direction out of the positive terminal of R2, then we have to denote Ohm's law in a different manner. This just standardizes that if this element is absorbing power, which it always will, then we want a positive resistance value, given that the current's flowing in a certain direction. Since that I've spoken about power abstractly, let's describe it quickly so that I can better explain the passive sign convention. So we denote power in its differential form, of course, as dW over dt. So this is the energy per second. So it's the rate of energy delivery or dissipation within an element in an electric circuit. And this is the units joules per second or watts, which we are mostly familiar with. The equation that we use for power is PVI. So this is the volts, the voltage times the current flowing through a resistor. Now we can substitute either V or I from Ohm's law to find three different versions of the power equation. Wonderful. Here we've obviously substituted V for Ri, and here we have substituted I for V of R, and we get this wonderful equation. So we can see that if we define the power absorbed within this resistor, if the current is flowing into the positive terminal, we can use the equation in the normal form. But if we define it flowing the current in the opposite direction, we again have to use the sign convention. So then this, or this minus symbol, negates this minus symbol over here. And it really just helps to minimize confusion within the circuit. Alright, as these things usually go, I was rudely interrupted by a lack of storage space. Okay, so I'm going to carry on where I left off. Unfortunately, this section has been filled in already, but I'm going to go slowly through it. Hopefully I can describe it adequately. So I defined two ideal sources. These are independent sources, so they will supply a constant voltage or current no matter what the rest of the circuit looks like. So we define the current leaving a voltage source out of the positive terminal. This adheres to the passive sign convention because this is in fact delivering power and not absorbing power. Similarly for the current source. Then we define 4 dependent sources. So this is a voltage dependent voltage source. So you can see we've defined a value Vx, mu Vs. So Vs is the voltage supplied by this dependent source. Mu is some scalar or nonlinear multiple, and Vx is some voltage elsewhere in the circuit. Ix, rho, Vs, so this is a current dependent voltage source. Rho again, some variable or nonlinear variable. Then we define a voltage dependent current source and a current dependent current source. So these are the 4 different kinds of dependent sources. Then we define the passive elements within circuit theory. We have a resistor, a capacitor, and an inductor. The resistor we've covered through this section and Ohm's law. The capacitor and the inductor we will cover in later sections. We define conductance as the inverse of resistance with the unit Siemens. This conductance value will become useful when we deal with inductors later. Then we did 2 simple examples. So here we define a voltage source with 100 volts. We define a resistor with 5 ohms. We define a current I alpha, and we define a voltage Vi. Here note that this I alpha is flowing out of the positive terminal of this resistance. So this is not essentially adhering to the passive sign convention. So we have to account for it. So when we want to calculate I alpha, we can use Ohm's law, but like I just did, the passive sign convention has not been adhered to. We have to utilize this version of Ohm's law. So I alpha is minus Vs over R. So minus 100 volts divided by the 5 ohms. Now we get a value of negative 2 amps. So this might be a bit confusing. How do we have a negative flow? And that essentially just denotes that the direction that we have defined is incorrect in terms of the passive sign convention. Well, incorrect is perhaps not even a best way of describing it. It's in fact that this direction, I alpha, is not in the direction that we have shown. So I alpha would in fact, according to the passive sign convention, be flowing into this positive terminal. If this had to be positive 2 amps, then this resistor would essentially be supplying power, which is, of course, impossible. So let's calculate the power absorbed by this 5 ohm resistor. We again, because of the sign convention, we have to use this version of the power equation, negative Vi. So we have minus 100 volts, which is this value, and then negative 2 amps I alpha. So this gives us 20 watts. So 20 watts is being absorbed by this 5 ohm resistor, as well as 20 watts is being supplied by this 100 volt voltage supply. Then we do one other example. Here we define a current source with a value of 5 amps. We define a resistor with a value of 0.1 Siemens, noting that this is the conductance and not the resistance. Then we define a voltage VB, positive terminal up here, negative terminal there. Let's first calculate the load resistance. So this is this 0.1 value. So we just do the reciprocal, we get 10 ohms. Very simple. VB. Now we have to be careful yet again, because the current, as we've defined here, flows out of the positive terminal, flows into the negative, out through the positive. So we have to use, again, this version of Ohm's law. So we use negative 10 times 5, so we have a negative 50 volt drop. So essentially what happens here, again, is that we've just essentially put our terminals on the wrong side. It's not essentially wrong, it's just that we need to stick to this convention, so we will get negative here. So if we had defined VB as positive here, negative there, this is VB prime, then this value would have been positive 50 volts, because the current is flowing in to this resistance value. Let's calculate the power absorbed by this resistor. We can utilize this version of the power equation, I squared R, so we have 5 squared, 5 amps squared times 10 ohms, we get 250 watts. And just for interest's sake, let's utilize this version as well, since we have the voltage as well. We have negative 50 volts squared over 10 ohms. So we have a 50 volt drop, or a negative 50 volt drop over VB divided by the 10 ohm resistance, and we get 250 watts, again absorbed by this resistor. So this lesson we covered the three fundamental variables: voltage, current, and resistance. We defined what resistors are, and we defined the relationship of these three concepts using Ohm's law. Noting that Ohm's law negates any kind of non-idealities such as heating or cooling, etc. We defined the passive sign convention, noting that the current of a passive element needs to flow into the positive terminal of that circuit element. We defined what power is and power in terms of the passive sign convention. We defined the ideal voltage source and the ideal current source, and we defined the four dependent sources. We defined the three passive elements, what conductance is, and we did two simple examples. Thank you.